Also today, we skip maybe to see other people's notes. I don't know.
Okay, so
Sound generic.
Silva from ETH Zurich can tell us about the role of complexity in finite quantum thermodynamics. And it's 2 lectures, one before lunch and one right after lunch. So thank you, Rob.
Thanks, Lydia. All right, this is great. This is the first time in 2 years that I'm having an in-person lecture. I realize that there are students from ETH Zurich that I've taught for an entire semester over Zoom. It's the first time actually having this. Right, so I'm going to speak about complexity, and the first thing I should say, because I realized once I wrote this topic and talked to a few people that complexity usually involves notions of computation. The notion of complexity I'm using here is more of, the dictionary meaning of how complicated a machine has to be in order to do a certain task. So from yesterday to today, we have looked at the foundations of many resource theories in thermodynamics. So we say this is allowed set of operations, and then we find out from those allowed set of operations and the states that we have bounds on what we can achieve or cannot, which are sometimes in the form of limits which are necessary and sufficient, sometimes just monotones which are necessary and not sufficient. But what I'm going to focus on in this lecture is really what was not explicitly done in many of those analyses, which is the actual machines that implement them. So in principle, when I write, for example, a thermal operation, where I have that this end state of the system is U system bath, rho system, some thermal state of the bath, U dagger, system and bath, and then trace out the bath. In principle, this is thermal. We can pick any Hamiltonian, but any Hamiltonian is actually a very, very wide freedom, because there's no constraint to the dimension, it is no constraint to the energy gaps. And any unitary is also automatically quite a wide constraint, because these are energy preserving unitaries in the case of thermal operations, but still they can get more and more complicated depending on what Hamiltonian we pick for the bath. So just looking at this sort of picture where we have a system, a bath, and a unitary that we apply on them, we can identify two sort of notions of complexity. One that involves the state of the bath, and this can be broken down into two things. One can just be the size of the state, which you can measure. Just let me know at any point in the back if I start writing too small and you start to miss it, because I might forget about this. So you can look at the size of the state as measured by just the dimension of the bath. Or you can look at the size of the state if you compose the thermal bath as a number of particles. So like say n qubits, then you have the number of particles. And they're not always interchangeable, of course, because you might have a composite system that is not a tensor product. On the other hand, you can have the allowed operations. And in this talk, I'm going to compare actually four levels of allowed operations, going from sort of the most powerful to what we would say it requires the least amount of control. The first level is just any unitary is operation. So this is now even more powerful than thermal operations. We say we still work in the case if we have a system, we have to pick something from the environment at temperature beta, but we're allowed to perform any unitary on it. Of course, the fact that we can perform any unitary on it comes at a cost. It means that we are assuming that there is some classical field in the that we are using as a device that can exchange energy with our composite system and bath. Will not exchange entropy because it's still a unitary operation, but it can provide energy. So in this case, we really look at the change in average energy as sort of the work cost of the operation when we perform such a unitary. The second case is to do thermal operations, but with a work source, with an ideal work source. So this is the case where you have row system, row bath, but now you also tensor it with another state. It's called eta of the weight. Oh, too low or too small? Too small. Eta of the weight, and so they are the usual way that we can think about this is when you have eta of the weight being a Hamiltonian, that's just an unbounded ladder. So you can write it discrete, but the easier way is also to write it as just the proportional some g times the x operator. So it's simply unbounded from below and above in energy. And the way to take thermal operations and use a weight is simply consider any two energy levels from the composite system and bath. If you had thermal operations, if these energy levels were not equal in energy, you would not be able to couple them. You would not be able to shift population from one to the other. But using a weight, you can do that. If I have any operator of E system bath, E prime system bath, where these are two eigenstates in energy of the system bath composite Hamiltonian, then all I have to do is to couple it to the translation operator of E SP minus E prime SP on the weight.
What do you think?
So
Of the index of the index.
Yes, okay. E minus E prime. I don't need SP. Yes. Right. So I'm not going to go to the details of like that this works, but suffice to say, if you choose a state on the weight that is sufficiently spread so that its entropy doesn't change when you introduce it into such an interaction, then you effectively are able to do any incoherent operation on the system and bath. So it's more general than thermal operations, but what it does not have is it still does not give you the ability to introduce coherences and to generate coherence if there wasn't any to begin with. Because I still assume that the weight state here is still incoherent. So it's a mixture, it's a distribution over energy levels that does not have any coherence. Okay, so that was the second one. The third one, now I have to go. Oh, let's see. Yeah, let's just see. Okay. Third one is back to energy preserving operations with a hot bath. And so now instead of the source of work being this ideal doubly infinite ladder, which essentially allows us to do any to couple to any two energies with zero entropy cost. Now what I have is I have a second bath at second temperature at beta hot. And so the assumption is what I can do now is I can take row system, can take any thermal state of the bath, and I can add any thermal state of the hot bath. And now these, remember this one is at beta, and this one is at another temperature beta hot. And by assumption, beta hot is less than beta because T hot is greater than T. So the hot bath is really, it's hotter than your environment. So it acts as a source of heat. And now I do a unitary on system, path, and the hot state. And this is again now like thermal operations, energy preserving on the entire thing. System, path, hot. And this tau v. Tau v is the thermal. So whenever I use tau, this is just to say it's the thermal state. So tau b is the thermal state at temperature beta. So this will be of the form e to the minus beta hb over the partition function according to that. So beta hot. Hot.
No, I'm asking.
Yes. Oh, sorry. Yes.
Beta hot is hot bulb, right? Then only beta is another bulb.
Yes. So I don't put beta cold or beta room. It's just if I just say beta without a index, it's like the environment temperature. This is sort of the temperature that you have really for free. You can always thermalize it. And I say that it's for free because in this case here, so in the first case, whenever we did an arbitrary unitary, we would look at the average energy. That would be our work cost. In the second case, when we introduce an ideal work source, then we look at the change in energy, average energy of the ladder. That would be our work cost. But again, because we're doing energy preserving operations on system, bath, and the weight, we can equivalently just look at the average energy change of system and bath, and that's already enough. And in the case when we use a hot bath, now the resource here is Q hot. The resource, which is the energy change in the hot bath. So essentially the energy change in tau hot in a single step would be, because that energy has to be provided by the hot bath if you keep repeating these the steps. Right, and then the fourth level, which is really the lowest control complexity there is autonomous machines. Autonomous machines are very similar to level 3 because what you do in autonomous machines is you have the same arrangement. You have a system, another system from the from the environment part and from the hot part. But instead of doing this discrete process where you perform a unitary, then you trace out the environment in the hot bath, and you bring back another copy of these, and you do another unitary, you essentially turn this whole thing into a continuous process. You turn the unitary into an interaction Hamiltonian, which acts continuously, and you take the thermalization and you turn it into a master equation. And in fact, one such example of this was done by Matteo in yesterday's talk, where he talked about the channel CT acting on rho, which gives 1 minus e to the minus gamma t on plus e to the minus gamma t on rho. So this was a channel where if you weakly couple to a thermal environment, then you gradually approach the thermal state. And this is, of course, you can write this as a master equation on just the state. d rho by dt is gamma times tau minus rho. So the advantage of the autonomous machines is that all of the questions about regarding what's the cost of like arranging all this sequence of operations. You reset the thermal state, then you bring a unitary, reset the thermal state, do a unitary. All of those go away because you simply switch on the machine at one point, and then you just let it run. You wait for it to approach a steady state, and the steady state gives you the thermodynamic properties of how the machine is doing, how much heat, and it's transferring to work, etc. The disadvantage, of course, is that it has very little control. So you really, once you set up the states of the bath and the hot in an autonomous machine, you cannot change them anymore. Whereas in principle, in the incoherent, in this paradigm, the third paradigm, each step I could use a different Hamiltonian from the bath and the hot system. Okay. Right. So at the outset, I'm going to say that the takeaway from the 2 lectures that I have today is going to be that in some cases, complexity does not matter if you are looking at, specifically you're looking at things like bounds to cooling and how, yes, Mark?
Sorry, when you're talking about 4 levels of the constraints,
Yes.
are there 4 different options on the constraints that we're imposing, or are we stacking one on top of the other?
No, there are 4 different ones, but I've arranged them in sort of order of how powerful they are. Because anything you can do with essentially the lower one, you can sort of do with the other one, at least in terms of the bounds of how cold or what state transformations you can make. Efficiency is a different question.
Okay, thank you.
You mentioned the ideal work. I would like to know what is ideal.
So an ideal work source, essentially the property that you want from a work source is that the energy change is that corresponds to delta S of work being equal to 0. So this is sort of the definition of work that I take, as opposed to, so heat is sort of energy change at the maximal entropy always, because a bath always obeys the maximal entropy principle. And a source of work, which is ideal, should have that the entropy change is 0. So what you do is you use a ladder, and you essentially need to use a weight that is so spread out that when you use it in conjunction with the system and bath, the spread is already so much that the mixture of different translations on the weight do not actually change the state so much. The overlap remains almost the same.
With this definite work, I would say the transition between two ideal states.
It's not deterministic work. It's actually in the opposite direction. So this is one of the tricky things in classically, when you have a weight, there are two properties that a weight has. One is that it's deterministic, and the other is that the entropy change is 0. And somehow, to me, at least when you look at the definition of Carnot efficiency, etc., it seems like the second one is the critical property. That's that the change in entropy is 0, not so much the fact that the work itself is deterministic. So this is a bit in contrast to, for example, the notion of work bits. They are a very different type of work because there the entropy change is not 0. Yeah. Okay. Yes. So as I was saying, for some things, complexity, a machine being complicated is going to matter. For others, it's not. And the first lecture is going to be where it actually turns out that the simplest machines are good enough to get results. I shall shift now to the other board.
It talks.
Yes.
So the camera follows it.
Wait, does it require my voice to?
Yeah, you can use your voice. Yes, there it is. Yeah.
Okay, so the first thing I'm going to start off with is I'm going to use the. Actually, how much time do I have left? Because I didn't.
You have half an hour.
So I'm going to use a very simple example to demonstrate the ideas that I would like. And that's the example of cooling a qubit. So my system is described by Hamiltonian. That's simply, well, ES times 1, 1, let's say. And I will use the following way of denoting Hamiltonians quite a bit. I just draw the energy levels. So this is the state 0, this is the state 1, and there's a gap ES in between them. And for simplicity, I'm going to assume that the system starts thermal at beta, so it's e to the minus beta HS by ZS. This is not such an important assumption. If you start somewhere different from thermal, you just have to change the analysis a bit to match that, but will not change the major conclusions that we have today. So that generalization is rather simple. And on the other hand, I have my machine, and this is now where I really start to fix the machine. So I say my machine is some Hamiltonian, but it's finite dimensional. So I could denote it by this is state 0 of the machine. And there are many energy levels until I have some Emax of the machine. And really the eigenvalue of that is Emax. So the highest energy eigenvalue of the machine from the ground state is Emax. And what I'm allowed to do, I start with the first paradigm. I'm allowed to take rho s, tensor tau of the machine, perform any unitary, and trace out the machine. And this is now my rho prime s. And there are two things I can do. I can either stop after 1 step, or I can repeat the process. And repeating the process does not mean that I throw away the machine state that I had after the first process, and I bring in a fresh copy from the state. So, or equivalently, I re-thermalize the state of the machine back into the Gibbs state at environment temperature. Okay, and so now the question is the first question is how cold can I get this state by doing such a process? So my goal is now to bring as much population from the excited state to the ground state in my system, and I want to know how far I can get by just using such a Hamiltonian. So a very simple example is to imagine that I didn't have all of the intermediate levels here, and my machine was just a qubit. So I just had ES, and this is my system, this is my machine. And what I could do is I could do the following very simple operation, which I call the swap, but in the language that Nelly used in the previous lecture, it's what you call a T transform, because it simply couples two levels. So it's a unitary that simply flips the energies of this, that, 0, 1, 1, 0. So if the system goes down in energy, the machine goes up, plus the rest does not remain changed. So I often, if the thing gets more complicated, I would simply refer to this as identity on the rest. It's meaning that you have a swap in some subspace, and on the rest of the density matrix, you do nothing. Yes, so if we did this here, I could write down really what my state change is, because I have P0, 0, 1 minus P. This is the generic state of a qubit of the system. This is the density matrix in the energy eigenbasis, so 0, 1, 0, 1. And this is tensor with some Q 0, 0, 1 minus Q, which of course is PQ, 1 minus Q, 1 minus PQ, and 1 minus P, 1 minus Q. And all that the swap does is it flips these two elements. So I end up with just the middle two terms flipped. Q1 minus Q, 1 minus Q, 1 minus Q. And that in turn is just the states having been flipped.
Anyone read? Yes. Okay.
P0, 0, 1 minus P. So the swap operation on qubits is very simple. By just, well, the swap operation on any two states actually has a generic form that it flips the states. And in this case of the qubits, you see now the state of the machine is now in the qubit, the state of the qubit is now in the machine. Yes, so it turns out that this is actually the best possible thing you could do with two qubits. If you simply had a system qubit and a machine qubit that started with more population in the ground state than the system did, and this would be guaranteed as long as your machine energy was larger than your system energy, then it turns out that this full swap is the best you can do. And the reason for that is actually from the theory of phasalization that you heard a lot about in the last lecture. Because once you have the initial state of system and machine, the eigenvalues are simply these four numbers. And any unitary operation that you do on a diagonal state, the eigenvalues of the final state are always going to be majorized by the diagonal elements that you started off with. And so as a result, if you wanted to maximize the ground state of the system, that would simply be maximizing this population in this subspace of the system, because when you trace out the machine, this is what contributes to the ground state of the system. So maximizing that sum there simply means bringing the largest elements out of your diagonal elements into that sum. So if your machine starts off with a larger ground state population in the system, then these two will definitely be the larger elements. In particular, this one will be less than that one, and that's why you do the swap between 0, 1, and 1, 0. So, right, so the conclusion is that for a qubit system, for a qubit machine, this is really the best that you can do. And what happens to the system at the end, if I write down what the final sort of effective temperature of the system is, because the states have been flipped, it means that the Gibbs ratio which is essentially, let's say, 0 rho system 1 upon 0, row system 0. So this is just the ratio of the excited state population to the ground state population. This ratio just swaps with the machine. Because the populations of the machine are now in the system. So whatever the ratio was for the machine in the beginning, that's on the system at the end. And the Gibbs ratio is also, one can write it for a qubit as e to the minus beta times the energy. So I can say e to the minus beta final, which is the final effective temperature on the system, times the energy of the system, is what the Gibbs ratio on the machine was originally. And that we know because the machine started in a thermal state, was just beta times E of the machine. Let's write it as E max. So this was the ratio of excited to ground state population of the machine to start with. That's now in the system. And so this gives us beta final indeed is equal to beta times E max by ES. Okay. Yes.
So initially they started in a different temperature, system and machine.
No, so they start in the same temperature, but because the energy gaps are different, the actual probability of being in the ground state is different.
Is that true to say that you are changing the degree of non-passivity of the joint system? For example, you start, let's say, in a maximally active state, you apply several thermal operations such that in the end, the state is less non-passive than it started because you are changing the populations. No, you are always swapping.
Yes, so it's actually, it's more non-passive. So the initial state, yes, because the initial state is thermal. If you look at the system and the machine together, it's a product of two thermal states, which means that the initial state is actually completely passive, not just passive. It's a Gibbs state of the joint Hamiltonian. But because we are doing a unitary operation, which allows us to permute any of the eigenvalues, we actually make it non-passive, because now we've sort of inverted in that subspace now 0, 1, 1, 0, we've actually put the higher eigenvalue on the higher energy state, which gives us the system in ground. Yes, essentially. So because the goal is to maximize the population in the system subspace. And so in doing this, we are going to make the joint system active. Do you have a question?
Compared to yesterday, you do not require the unitary to be energy preserving.
No. So in this case now, I'm considering that I do have a source of work that allows me to do any unitary, even in this case, even coherent unitaries. So and I simply take into account what the cost is by looking at the change in average energy at the end. Yes. Right. Okay. So this is the result for the qubit. Now, here's the first takeaway of where complexity doesn't matter so much, which is that if instead of having a qubit, you had all of those energy levels in between, you would in fact still have this, but just with an inequality here. And again, the proof of this is by majorization, and I can give you an intuitive reason as to why. If you look at the joint state of the system and the machine, where again, the system is first. So this is really the 0, 0 subspace of the system, the 0, 1, 1, 0, and so on. What we start with some density matrix, which is of course just the product of thermal states of system and machine. And what we want is the sum of these elements to be the largest possible. And so what we do is we just look among all of the diagonal elements. The initial state, of course, is diagonal. And the best possible thing to do is simply to make the permutation where the largest from among the diagonal are here. And so every now and then, every time you flip one from here to here because it's larger, you end up doing a T transform or a simple swap with respect to those two energy levels. So something of the form 0 on the system, EI on the machine, with 1 on the system, EJ on the machine, plus of course the Hermitian conjugate. And every time you do that, you will take beta final towards a certain temperature, which is always worse than this, because every Gibbs ratio in the machine is going to be less extreme than the one between the ground and excited state. So if I look at the Gibbs ratio, the ratio of the populations in the maximally excited state to the ground state, this is the smallest number. If I pick any other state, I will get a higher number, which means that all of these little operations essentially try to take beta towards different temperatures, and you get a mixture of all of those effects. And the greatest effect is, of course, when you swap with the ground to the excited, the biggest subspace of the machine. So in other words, the bound of how cold you can get this qubit to be is actually determined by not any of the like complicated structure of the machine, but simply by the gap between the initial and the final state, the minimal energy and the maximal energy. One thing I should say is that if you do this for a single time, so if you do the operation a single time, then of course the best possible cooling is going to be something in between beta of the system originally and this maximal upper bound, because you just find the best permutation, you will get something in between. But the interesting thing is if you repeat the operations and you're allowed to repeat it as many times as you want, what happens eventually is that all of the other levels stop helping you to cool until it really becomes only the maximal to minimal energy of the machine that actually matters. So in fact, this beta final, beta Emax upon ES is a tight upper bound on what the final temperature of the system can be in the case of arbitrary dimension and unbounded repetitions. Yes?
By repetition, do you mean we thermalize the machine after each step?
Yes, indeed. If you don't thermalize the machine after each step, you're basically in the same step because you're still doing a unitary which you can compose with your unitary that you just did. Yeah. Yes. Okay. So yes. So the end conclusion indeed is that for the cooling bound, right, the only thing that matters is the initial to final thing. And one of the immediate generalizations you can do is you can take HS to actually be a more complicated Hamiltonian and then ask, well, if I do now the same thing, I can do any unitary between system and machine and repeat the operations, then what am I going to find is the coldest possible state, so the one that is most weighted towards the ground on the system. And it turns out that essentially this Gibbs ratio e to the minus beta final ES, if I call this ratio G, the coldest that I can get the system to is a state in which every Gibbs ratio is actually G between successive states. So my bound rho S star somehow is just G to the N, En, N upon, of course, the corresponding normalization. So it's essentially a state where it looks like I essentially applied the machine, the ideal version of the machine, to every successive pair of energy eigenvalues. And so this somehow also demonstrates the power of looking at T transforms, because they're not only the basis of many operations, they also, if you pick the best possible T transform, the best possible swap, you end up getting what the bound will be in the very general sense.
Is this rho star in a thermal state at the end?
Sorry?
Does this rho star S have to be in a thermal state at the end?
No. So they, I mean, it would, the Gibbs ratios are constant, but that would only correspond to a thermal state if the energies were also constant.
Yeah.
So in fact, yeah, the effective temperatures that you would see in each transition would actually be different.
Yeah, that would, yeah.
But
Defining a temperature for the entire system would be
very difficult. Yeah. So in this paradigm that I've talked about, the easier way to talk about bounds is not by temperature, but by majorization. So the technical way of saying this is that rho star S, at least when you look at the eigenvalues, the diagonal elements, this majorizes any rho prime that you can get from here. So if your initial state rho S is majorized by rho star S, then as many times as you repeat this operation, you will always be majorized by rho star S. And this in combination with showing that you can actually approach this state in many operations shows that it's a tight bound. This is really a cooling bound and it's tight. You can approach. Okay, now you have to turn to the other side. All right, I will speak now. So all of what I've done now is for the paradigm in which I could do anything. So what I would like to do now is to consider okay. now I'm going to consider what happens if I decrease the amount of control that I have. So this is going to be the effect of control complexity on the cooling bound. So the first thing to consider is.
So before can I ask you a
Yes.
question? So there, why is majorization and not thermal majorization? Because I would expect that it would be thermal, you have some temperature.
Yeah, so the key with thermal majorization was that there, because you were only allowed to apply energy preserving unitaries, you could only work in degenerate subspaces of system and bath. And so because of that, you always, instead of comparing just the population of the system, you have to compare them after multiplying by the corresponding Gibbs ratio that makes it degenerate. In this paradigm here, we can mix any eigenvalues. So it sort of becomes closer to noisy operations in that sense, because I have complete freedom over the eigenvalues. So in fact, if you write down the effect of a general coherent operation on a diagonal state, it is actually, if you just look at the diagonal elements, it looks like a doubly stochastic matrix on the original diagonal elements. So when you don't care about the off diagonals. So this is why it sort of reduces to majorization and everything that Nelly had spoken to before.
I have a question. So suppose you are cooling a system by a very high dimensional machine,
Yes.
and on the other hand, you are cooling a system by repeated interaction with a qubit. So are they equivalent? So the effective cooling of the system is equivalent, or in one case you will have the better cooling and another case you have the.
If I keep repeating the interactions and the first machine had the same maximum energy gap as the qubit that you use in the second case, then the bound is the same on both of them, because it only cares about the maximal bound. What is different is, and this is something I will speak in the next lecture, is the energy cost on the way there. So that is where the intermediate energy levels help by decreasing the energy cost. But this is something, yeah, I'll speak about in a second. But the cooling bound indeed is the same. Yeah. Okay, so now the question is, so in paradigm 2, which was, as I said, the ideal work source, the question is, can we achieve the same cooling bound? And the answer is yes. Yes, the same bound. And the reason is that, so the key difference between the first and the second paradigm is really coherence. In the first paradigm, I can do any unitary operation. So I could leave my state with lots of coherences between non-degenerate energies. In the second paradigm, I consider that I can couple different energy levels, but it's incoherent once I trace out the way. However, the cooling bound doesn't really care about that. The best possible operation when it comes to cooling is a permutation. I just permute my energy eigenvalues. So when it comes to a cooling bound, whether I use arbitrary unitaries which are coherent or incoherent unitaries where I can only swap energies without introducing coherences, it doesn't matter, because coherence, and when I say coherence, I really mean between non-degenerate energy eigenvalues, because between degenerate eigenvalues, of course, even energy preserving operations would give you the same. Okay, and the next thing to do is the third paradigm where I use hot bath, and now I stick to energy preserving operations, because I do not, my source of energy is now not an external classical field, but actual energy preserving operations with a source of heat. And here the answer is it does change. And it changes in the following way. So I return back to the example of if I just have a qubit here, and now I know that sort of to do the cooling bound, to cool the maximum this qubit, I really don't need to add any other energy levels in my machine. But the problem is now I can no longer do the swap that I mentioned at first, because clearly this is not an energy preserving operation. They're two different energies. And so the way to make this an energy preserving operation is to add a qubit from the hot bath that is exactly the difference in energies as is. So this is now hot, and I choose E hot to be E machine or E max, let's say, because I've called E max there, minus E system. And the result of this is that there's the new unitary that flips both the hot and the system down and the machine up is now energy preserving again, plus the Hermitian conjugate, plus identity on the rest. So this is the new unitary operation, the new swap unitary that I would do in this paradigm. And now here the result changes a little bit, because when I just derive the formula for beta, what I said is that the Gibbs ratio of the system S basically takes on the Gibbs ratio of the system of the machine by doing the swap. But here the system is not really interacting with just the machine M alone. It's interacting with a particular subspace of the machine and the hot bath. So if I write these two as a single system, then I have something like this. So I've written it as a 4-level system, and these are the states 0, 1 mH and 1, 0 mH, and these are really the ones that interact with the system. So if I look at the swap in this new picture, it's a swap between these two states, which by definition, because I've chosen the energies to map, have exactly the same energy. So the Gibbs ratio of the system, instead of going to just the Gibbs ratio of the machine, is going to go to the Gibbs ratio of this composite system here. And this is very easy to calculate. I take the ratio of these states. So if I say the ratio of 1, 0, tau machine, tensor tau hot, 1, 0. Yes, too small?
That's super funny. Thank
you. 1, 0, tau machine, tensor tau hot, 1, 0 upon 0, 1, tau machine, tensor tau hot, 0, 1. Because it's a product state, this just factorizes into the Gibbs ratios 1 upon 0 of the machine, of the M, so the part that's connected to the environment, and 0 of 1 of the part that's connected to the hot part. So this is the product beta E max times e to the plus beta hot.
It's at the same temperature, right? Is everything at the same temperature?
The hot part is at beta hot. So that's a different temperature. So beta hot times E max minus EX. Because it's beta hot times E hot, I've just substituted E hot there. So what we find is that if I now, and this is now, this is what e to the minus beta final ES is sort of swapping with. So the result is that the new condition is that beta final ES goes to beta E max, which was like before, minus this contribution. Okay, so the conclusion is that by lowering the control complexity, by saying actually I don't just allow myself a perfect classical field where I can do unitaries or even an ideal work source, but I force myself to use another equilibrium resource, another thermal bath as my non sort of thing that's not in equilibrium with the environment. Then the cooling bound becomes strictly worse, because this is the higher the beta is, the colder it is, and now this is a strict reduction in beta final. And so that's one of the conclusions. The second conclusion is that, so in the case of a qubit, when you do a qubit swap, you really flip the states perfectly. So you get that the machine state becomes the system state, and so the Gibbs ratios immediately swap. But in this case, because the swap is not between the system and an entire qubit, but rather a subspace within the joint system of M and H, it means that a single swap is not going to take the Gibbs ratio of beta final ES directly to this final quantity. A single swap is going to take you somewhere in between, because there's a probability of not even being in that subspace. And so you get somewhere in between your initial beta and your final beta. So the two things that you end up with here are that you have an increased number of operations, or time, if you take number of operations to correspond to the time of the thermodynamic protocol, because you have to repeat the step that was a single time in the coherent case many times here, and you also have a reduced cooling bound. Note that the reduction in the cooling bound is not it's not a very strict one, because if you have a hot temperature bath that becomes hotter and hotter, so to the limit where let's say you have a maximally mixed state, so a temperature, hot temperature bath where beta hot goes to 0, which is T hot going to infinity, then of course this vanishes and you end up back with your cooling bound initially, which really corresponds very much to the case of a ladder which is unbounded up and below. Yes?
Is this general that you can always do, you can only do worse with this framework than with the unitary?
Yes. Yeah. So the general statement is that once you fix the Hamiltonian of the machine part, then no matter what you introduce on the hot part to plug your degeneracies, you always end up bound by this formula, because the energy, once all that the hot part can give you is really plug the degeneracies, but the Emax, the highest energy gap to a machine, is what gives you how much you can get colder.
Sorry,
Science now.
you said increasing the number of operations in the sense that now you have a three-body interaction.
It's because in the three-body interaction, your system, the swap, if you look at it as a system swapping with something, the qubit of the system does not swap with the full qubit like it did in the initial case, with a virtual qubit, and because so that means you don't go all the way to that state in one operation. Yeah.
Good time to stop.
Okay, so trying to conclude then. Well, okay. Right. So indeed, so that the thing that I want to say then at the end of this one is, just when it comes to cooling a system, like the upper bound of how cold you can get the system, the simplest machines actually do very well. You do see a difference when you take different control complexities, so going all the way from arbitrary unitary operations down to the incoherent operations. I should say that if you now go down to the autonomous machines, you would essentially fix a diagram like this and then make it a continuous machine, so it would be very similar. But indeed, the cooling bound itself does not care about using more complicated machines. And when it comes to efficiency, because we have not talked about the work cost of any of these operations, that's a different story where complexity starts to matter, and that you require full time of much to consider.
Okay. Thanks, Ralph. Let's have lunch.